14.3, possibility. Now, what do I have over here? Let's say, if humidity makes it so the temperature is higher than it really is. Okay. Alright. So in dry air, we actually see the temperature to be lower than the thermometer indicates. Okay. So here's the. I'm going to ask someone else to read it. Hey, Chester, can you read from here to here?
The National Weather Service has devised the heat index, also called the temperature humidity index, in some countries. It describes the combined effects of temperature and humidity. The heat index, I, is the perceived air temperature, where the actual temperature is T, and the relative humidity.
Okay, thank you. So, Jack, could you read from here to here? From here.
The heat index I is the perceived air temperature and the temperature is T and the relative humidity is H.
Okay. Alright. Matthew, could you read from here to here?
So I is a function of T and H, and we can write I is equal to that function of T over H.
Okay, great, thank you. Maybe clear this.
So the following table of values of I is a vector from a table compiled by the National Weather Service.
Thank you, that is good. We have Bahrain alert. Okay, all right. So here's the table. Okay. So in this table over here, we see that this term over here is for the actual temperature that you can read from the thermometer. And the row here is for the relative humidity. Thank you. So, for example, let's look at the highlighted row and column right here. Okay. So the humidity, say it is 70%. So suppose we have a humidity of 70%, and we're considering the heat index as a function of a single variable T. So suppose we fix it. So let's fix the humidity, we consider only 70% humidity. And then we let the actual temperature here vary. Okay, so the actual temperature can be 90, 93, 94, etc. Okay, but we fix the humidity here to be 70. This heat index, the heat index that we're looking for is actually a function of this variable T, because the humidity here is fixed and we let the T vary. So it is a function of T only because we fixed the humidity. So the heat index, so this heat index over here, when you fix this humidity and let this first variable here vary, okay, then that is a function of this variable only. And let's call that function here G of T, because this one can fix, so it's not going to change. So let's call that function G of T only. That's the only variable in this case, because that is fixed. Okay. Now, what is this one? G of T here. That describes how the heat index increase as the actual temperature increase when the relative humidity is 70. So when the relative humidity is fixed to be 70, then the heat index, back over here, how does it change? Okay. As the actual temperature change. Now, the word T of G, when T is 96 degrees Fahrenheit, is the rate of change of the heat index with respect to the T only. Okay. When T is 96 degrees Fahrenheit. So G pi of 96. Okay. G pi 96 here is actually the rate of change of the heat index. It's the rate of change of the heat index with respect to T ohm, with respect to its T ohm, G power T. Okay. So when the actual temperature is 96 degrees Fahrenheit, what's the rate of change of that? Now, do you remember from what is it? Right? How do you define the fluidity at 96? Is the limit, remember the definition of the fluidity, is the limit of H approaching itself, and that we should put a difference quotient here. What is that difference quotient? E of 1. X plus H, but in this case, X here is what? 96. So 96 plus H minus G of 96 and over H. Yes, we got it. Good job. Now, because G of, what is G of 96? G of 96 is F over. Because G of 96 is, you just put, what's G of 96 plus H? Well, you just put this, that's the temperature, that's the actual temperature, right? And put that in the first component. So we're going to put F of 96 plus H over here. Okay. And remember the second component, the humidity is fixed to be 70%. We're not going to change it. The only change here is the first component. So 96 plus H is going to put here, and then 96 put here, and then over H over here. Okay. So that's how G prime of 96 is defined in terms of G here and in terms of F here. So basically, you fix the other component, okay? And then you let this one here value. So it's the same concept as the definition of the T before. Now, remember, we can actually approximate the duality at 96 by taking the nearby value to calculate that, right? So if you try to find G prime of 96, then what we can do here is we can use the table. We can use this table over here, and we can use the y2 minus y1 over x2 minus x1 using the function value at 94 and 96, and using y2 minus y1 over x2 minus x1 to get this value over here. So near 96, we take 98, and then y2 minus y1, x2 minus x1, p2 minus 1 will be 2. So we'll do this one here, and we got those numbers here from the table. Okay. This one here is this one here is this, and the change in T is 2, we got 4. And then we also take, well, below 96, let's take 94. Look at the function value at 94. So you can use y2 minus y1 over p2 minus p1. So that's -2. You can 94 subtract 96, -2. And we got this number here, 3.5. So those are the approximation to G prime of 96, using those values in the table. We do that. Now, what we do here is we can actually take the average. Take the average of these two. What's the average of these two? You add them up, and then what? Divide by 2, right? Well, you can see right away. It's 3.75, right? In between these two. So 3.75. So that is going to be an approximation to G pi of 96. And what does it mean? This means that when the actual temperature is 96 degrees Fahrenheit and the relative humidity is 70%, remember we fixed the second component to be 70, and then we let the temperature here vary, then the apparent temperature, which is the heat index, is what? The G pi 96 is about 3.75. What does it mean? It is a pocket number, so this remember the routine indicates the rate of change, right? So the rate of change is positive 3.75. So the heat index is going to go up or go down. Go up by how much? 3.75. 3.75. And what would be the unit?
Get that. For
So down here is degree, right? It's a degree. Okay. For every degree, that the actual temperature rise. So this is called the actual temperature rise. And for every degree that the actual temperature.
so the heat index is going to rise that way. So what does it mean?
So in this point here, you see that the humidity is 70%. It's kind of humid, right? So for every degree the actual temperature go up, say the temperature go up only 1 degree, then you actually feel that it go up 3.75 degrees because it's kind of humid. Okay, so every 1 degree rise in the temperature, you feel that the temperature go up like 3.75 degrees. So that's what how it is. That's the meaning of this. Okay, the next one over here, we're going to take a look at this time, instead of fixing the humidity, this time we're going to fix this actual temperature. Okay, so we're going to look at this row over here. So 96 degrees over here. And we're going to let the humidity vary. So it could be 50%, 55%, 65% humidity, etc. Now, the duality of the function when the humidity is 70%, okay, right here, okay, is the rate of change of heat index with respect to the humidity. So it's G pi of H, which is G pi of 70. So G pi of 70 actually is the rate of change of heat index with respect to the H, and when H is 70. So what is it? That means for when the humidity is 70%, then if the humidity go up 1 unit, then how much does the heat index go up? Now, according to the definition for duality, it's the limit of a different constraint. What difference quotient should I put? G of what? 70 plus H minus G of 70 over H. That's the definition for
Duality. Okay, good job.
And because we fixed the temperature to be 96, So the first component, this first variable here, we're going to fix to be 96. Okay. Remember, this g here is a function with this first component fixed to be 96 in f. So all you have to do is put 70 plus h over here, 70 over here, and then h over here. The first component is fixed to be 96 in this case. Now, just like what we have done before, we can approximate this to a t using the nearby data. Okay, so if I try to find g pi of 70, I can take g of 75 subtract g of 70 and divide by 5. It's like y2 minus y1 over x2 minus x1. Right? Use that. And I got 1. And I also take another nearby data values, g of 65, and then g of 70, and then the change in the h here is -5, and I got this number, 0.8. What's the average of this? This here? It is 0.9. And what does it mean? What does this 0.9 mean? This says that when the temperature is 96 degrees Fahrenheit, when it is fixed to be 96 degrees Fahrenheit, then the relative humidity is 70%, then the heat index go up or go down? Go up because it's positive, right? Go up by how much? 0.9 degrees for every 1% rise in the humidity. So when the humidity go up 1%, and then you feel that the temperature go up by 0.9 degrees. Okay. So the heat index is going to go up 0.9 degrees for every percent that the humidity, right? This is the H here is the humidity. For every 1% the humidity go up. So when the humidity go up, you feel the temperature actually is rising, even though the thermometer doesn't say so. Okay, so it's more humid. You feel that the temperature is go up. Okay. Now the idea of partial duality. So this is an example. Okay. So if you have a function of two variables, x and y. And suppose we let x value and keep y fixed. So that was the example we have done, right? We keep one component, we keep one variable fixed, and then we let the other variable vary. Okay. So say the second variable, the y here is fixed to be c. Then we only consider a function of a single variable x, because the only change over there is the x. The y is fixed. And then we call the new function g. Then the duality of this a is called the partial duality of the function with respect to x b comma b. So if you fix b and let x here vary, then the g here, if it has a duality at a, then the partial duality is denoted by this. So g pi of a is, well, first of all, what is g? G over here is just keeping the y here fixed to be b, and here change this. Then g pi of a is actually the partial duality of the function with respect to x at this a comma b. So only this x here is changed. This second one here is fixed. So I highlighted the one that changed. This here is changed.
So by the definition of duality, what's G pi of A? So today we go over and over the definition for duality. What should I put as this quotient here? Limit of G of what? Well, A plus H minus G of A over H, right? Okay. And what is the G? The G over here is just the function f having the second component fixed to be B. So now all you have to do is just put this A plus H in the first component, this A here in this first component, and then over H. So this is the partial duality of the function with respect to x at A comma B. You see over here, only this first component, the x component will change. So we're similar idea as what we had before, except this time we keep the other component fixed. But this one here is A plus H, and here's A, and here's H. So that's a connection between the old definition and this. So that's a partial derivative function with respect to x at A comma B. Similarly, if the partial derivative of the function with respect to y at A comma B, what do you think you should put over here? This time we're going to fix this A, right? The A here is fixed. So we fix this A, fix the first component, and then we have the second component value. Okay? So it's the possibility is like y, the y component value. Okay? So the first component will fix is the A, and what should I put over here? B plus H, and here B, and here H, right? Okay, good. B plus H, that. So we start with this having before. It says that the heat index, the function, the possibility with respect to the temperature at this point, when you it's going to be 3.75 for every 1 degree. The actual temperature go up. You feel like the temperature go up 3.75 degrees. And the possibility of the heat index with respect to the humidity at this point is 0.9. And what does it mean? That means for every 1% that humidity go up, you feel the temperature go up 0.9 degrees. Okay. So that is the definition. Well, let's try to write it one more time. Okay. So what is this? This one over here, the partial derivative of the function with respect to x at A comma B is the limit of what? Everyone? F of what? Yeah, which one is fixed in this case? In this case, remember, possibility with respect to x, then the y is fixed. So you keep f of the second component is going to fix on b. Okay, both of them. Okay. So we're going to have this. Yeah, I think you guys said it. Okay. So possibility with respect to x, the second component here will fix on b. And then here's A plus H. Okay. And then the second one, what should you put here? Everyone? F of A comma B plus H? Yes, you got it. Okay. So over H. So that's the one. That's the definition, partial derivative. Now, if you're doing so well, this one here is similar, isn't it? Right? So partial derivative with respect to x is the limit as h approaching 0. What should I put here? F over x plus h. X, right? Here's h. Okay. What about partial derivative with respect to y? This time we're going to keep the x here fixed. So the first component is not going to change. Stay as f. And here you put it. Y plus h, y, and here's h. Okay, so that's the partial derivative of the function with respect to x and the y. Now notation here. There are many notations for partial derivative. This is I did before, right? This one here is kind of common. How do you read this? Okay, this one here we call that partial derivative of f with respect to x. But it's kind of long. And some call it del f, del x. But then sometimes del has other meaning. Maybe you guys can do a research on that one and put it in the discussion. How do you say this? Maybe you can find some interesting idea. I have some question about it. Because when I say partial derivative function with respect to x, it seems like a very long sentence, right? Okay. Then I would like to know maybe some short way to say that. Okay, so that is one way to denote partial derivative function with respect to x. And also you can put the fx here. That stands for partial derivative function with respect to x. And you can also put f1 here. That indicates because x here is the first variable. Okay. And then you can put p1 and then f over here. They stand for differentiation with respect to the first variable. Okay, and those are the equivalent notation, all of them. Okay, and then for the y here, y is the second component, the second variable. Then we put a 2 here, 2 here. Those are equivalent notation. Now you will be very interested in how to find partial derivative, right? How do we find partial derivative? It's actually quite simple, don't you feel? Because if you know how to find derivative, you know how to find partial derivative. So to find partial derivative with respect to x, you're going to regard y as a constant, and then you can just differentiate that with respect to x. Just think about y here as a constant. And similar for partial derivative with respect to y. So now let's try some example here. Okay, this first example. So take a minute to try this on your own first. Okay, how about we do one of those together? In order to find the partial derivative of the function with respect to x at this point, we first find the partial derivative first, right? Okay. So what is the partial derivative of this function with respect to x? Okay, let's take this term by term. Okay. So let's take this term here. What's the derivative of this with respect to x? That would be 3x squared, right? Okay, good. Now, what's the derivative of this with respect to x? Now, in this expression over here, the y squared over here is considered as constant. Okay. because we are differentiating with respect to x. So we're going to keep this y cube x. So when we differentiate x squared times y cube, that this is just like a constant times x squared. What's the derivative of that? Okay. Do we need to use the product rule? No, you don't. Okay. What happens when you have a constant times x squared? For example, if you have x squared times y, so the x squared times y cube here, this y cube is kind of like the 5, okay, because it's like a constant, okay. We're taking derivative with respect to x, so the y cube here we think about it as a constant. So what's the derivative of x squared times y cube? Yes, thank you. So that will be the derivative x squared is going to be 2x. And then this one here is just a constant multiple of that, right? Then we just multiply it with that. So then we'll get times y cube. Okay. Just keep that. If you take the partial derivative with respect to x, think about the y here is fixed. Okay, you're doing so well. Let's finish the last one. This is negative 2y squared, but we're taking partial derivative with respect to x. This one here is regarded as a constant, right? Well, what's the derivative of a constant? It's going to be 0, okay? So therefore, when you take the derivative of that, it's going to be 0. So the partial derivative of this function with respect to x is going to be 3x squared. Here's a plus, okay? So plus 2x times y cube, and then plus 0. Well, we don't need to write it 0 here, right? So just we got the other one as a constant. Okay. Now, you guys, after you take the partial derivative, now we can try to substitute, right? So what is the partial derivative of the function at 2, 1? Then you will just substitute. Substitute x to be 2, y to be 1, and just plug it in here, right? And substitute here. So x is 2, 12, okay. And then plus 2 times 2 times 1. Well, is this 16? I hope I don't make a mistake. Is that where you got? Let's see. All right. Yeah, that's 16. Okay. Now, can you guys finish this by doing the partial derivative function with respect to y? Okay, you guys can tell me, what's the partial derivative function with respect to y? When you take partial derivative function with respect to y, you hold which variable fixed? You hold the x fixed, right? You fix the x. Think about x as a constant. Okay. Take a minute. Okay, tell me what you get. What do you get? Raise your hand if you know the answer. Somehow my screen here. Okay. All right. Raise your hand if you got the answer. You got the answer? Okay, good. Kenny, what do you get? Yeah, you're raising your hand. You got A? Okay. All right. Let's check this out. Okay. This time when you take the possibility with respect to y, you're gonna think about this x here as constant, right? So let's try this. With respect to y. Okay, let's take a look at the first one. What's the duality of x cubed with respect to y? 0. Good. Okay, and then in this one, we're going to, because we're differentiating with respect to y, we think about the x squared here as a constant, right? So what's the duality of this? Right, x squared is a constant, so it's constant multiple, so times. Now we differentiate y cubed, the duality y cubed is what? 3y squared, we got it, good. Okay, finally, what's the duality of this negative 2y squared with respect to y? This is negative 4y, right? And then now you can just substitute 2, 1 in it. So the partial duality of the function with respect to y at 2, 1. So that will be, and you do the algebra, okay? And what did you get? Somehow my Apple Pencil doesn't work very well today. But okay. There's a delay on the showing those. Anyway, it's always going to go faster than the. My screen just freeze. I'm going to. Is the Wi-Fi good? Okay, just take a moment to think about what we have learned, right? So when you take partial duality with respect to x, you can just think about the y as fixed, as like a constant. When you take a partial duality with respect to y, you think about the x as fixed. Okay, all right. Okay, now it's finally working. Let's see. Okay. So the result here, it is equal to 8. Yes. Kenny, you got it right. Okay. Okay, good job. You guys just take the first partial duality. Now, interpretation of partial duality. Okay, how do you interpret that? Sometimes it's good that you can visualize it, right? Okay. So over here, you see this is the surface. This is the graph of a function of 2 angles. Now, first, we're going to, well, at a comma b here, when x equal to a, y equal to b, then we have this one right here, this point p right here. Okay. And the z coordinate is f of a comma b equals c. So the c here is the function value right there. So first we're going to fix the y. So we're going to fix the y here to
b, how do you fix the y to b? Well, you just take the y equal to b. Y equal to b is this vertical plane over here, and so y equal to b. And you take this vertical plane over here, it slices. When you slice it with the surface, it results in this curve over here. So we go this way, without the intersection will be this curve, C1. Let's call that C1. Okay. The possibility of the function at this a comma b is actually the slope of the tangent of this C1 over here. So remember the word b corresponds to the slope of the tangent. So the possibility with respect to x at a comma b corresponds to the slope of the tangent of the intersecting curve C1. When you take the y equal to b and intersect with the curve. So that's the slope of the tangent of C1 when you fix the y to b. Now, what happened to the other one? Possibility with respect to y. So what is this one? This is possibility with respect to x at a comma b. Then the possibility with respect to similarly, okay. Now what about the possibility with respect to y? Then you're going to take x equal to a, like this thing over here, virtual twin, and then you intersect the surface in a graph, let's call it C2. Then the slope of the tangent of that curve is going to be the possibility of the function with respect to x at a comma b. Okay. So it's a slope of the tangent of the intersecting curve right there. Now we'll actually have the C2 here indicated. That's the C2. And when x equals to a intersect at the C2 up here, then the possibility of the function with respect to y is the slope of the tangent of C2. Okay. Interpretation of possibility. So if z equal to a function of two variables x and y, so the possibility is z, right? Remember z equal to f of x and y, okay? So you can sometimes instead of writing this way, possibility of function with respect to y, you can also write it this way. You can also write it possibility of z with respect to y. This one and this one, you can interchange them if the z here is a function of x and y. Now, what does this one here represent? It represents the rate of change of z with respect to x. Okay, with respect to x, when which one is this? Or when y is this? Yeah. What are we thinking here? Possibility z with respect to y represent the rate of change of z with respect to y, where what is this? X, right? That's x is space. Okay. Okay. Okay, let's try one more example. We have this function and we try to find possibility with respect to x, with respect to y, that is 1, and interpret this number as slope. Okay. Can you find possibility of this function with respect to x? You guys try? What do you get?
Let's do it together. What is the what's the partial duality with respect to x? Let's think about this term here. When you take the partial duality, this one here get 0, and then here you get what? Negative 2x, and then this one here you get 0. So that will be negative 2x, right? Now what about partial duality with respect to y then? This one here you get 0. This one here you get 0. Yes, because when you take partial duality with respect to y, you think about x here like a constant, and the duality of constant will be 0. And then what's the duality of this with respect to y? Negative 4y, right? So it's negative 4y. Good. Now after that, if you try to find the partial duality at this point, then you can just substitute x to be 1, y to be 1. So you get this and this. Okay, the substituting. And how do you interpret this? To interpret this,
You see, this is the graph for the function. And at 1, 1 down over here. And then the corresponding point on the graph will be this one. Now, when you take this vertical plane y equal to 1, you take this vertical plane y equal to 1 and slide this surface, you get this curve over here, C1. The slope of this curve here is equal to what? What's the slope of this curve? Can someone tell me? What's the slope of this curve at this 1, 1 at this point? What's the slope of this curve? The tangent line to this curve. Remember here you fix the y, right? The y is fixed, and you let the x over here vary. So that will correspond to the partial duality function with respect to x at 1, 1. So the slope of this tangent here is negative 2, okay? So that's negative 2. What about if you fix the x to be 1, then when you take this vertical plane x equal to 1, it's going to intersect this surface here, resulting in this curve, this intersecting curve, C2. What's the slope of the tangent of this curve at this point? 1, 1. And 1, 1, 1, 1. What's the slope of this tangent? Negative 4, yes. So that will be negative 4, okay. So think about partial duality as the slope of the tangent of those C1, C2, etc. Those intersecting curve. Function of more than 2 variables. Okay, now we have done function of 2 variables, right? But now we can go function of 3 variables. This time the definition is kind of similar. If I function 3 variables, partial duality with respect to x is the limit of what? Well, when you take partial duality with respect to x, the y and z will be fixed. So you take y and z, and then you would change the first component, right? The first variable. What should I put over here and here?
X plus h and
X plus h and x over here. Yes.
So only the first variable here change. So yeah, you got it. Okay, good job. All right. So in general, you can actually do that for partial duality with respect to the I variable xi. Then you would keep all other variables here fixed, and you would change the I variable, right? So from xi plus h to xi and here over h. So all other variables considered as fixed. Only that variable here change. And here's some other notation for puzzle. So you can get all those notation. When you see them, you know that they mean the same thing. Okay, now let's try one example. We have a function of three variables here. Let's find partial derivative with respect to x. Yes, that's how I'm going to do over here. So if you try to find partial derivative with respect to x, you're going to think about the x. You're going to think about the y and z fixed, right? Okay. So e of x, y, ln of z. If we try to find the partial derivative with respect to x, then you can think about the y and the z here as constant. Okay. What will be the partial derivative with respect to x here? Can someone tell me? Yeah, you got it. Good job. Okay. And how did you do it? Okay. Someone say, "Oh, I'm a little bit rusty on differentiation. Can you go over this in more detail?" Yes, we can do that. Okay. So first of all, this function here, this is multiplication. Okay. And you multiply with ln and z because we're taking derivative with respect to x. Then ln and z as a considered as a constant multiple, so we can go ahead and put ln and z here as a constant multiple. And then we're going to take the partial derivative of this e to the x times y with respect to x. Okay, so think about take the partial derivative xy with respect to x. When we do that, what would that be? This one here, we need to use the chain rule, right? We need to use a chain rule. So ln and z will be outside. Okay. What's the derivative of partial derivative of e to the xy with respect to x? Well, this is e to this function. Consider that as a function, say u, right? So the outer function is that exponential function with base e. So the derivative of that is what? E to the is that exponential function itself. So e to the x times y. But by the chain rule, we have to multiply that by the derivative of this inner function. What's the derivative of this inner function? Xy with respect to x. That will be y, right? Yeah, so it's y. Okay, so you're using, first you use the constant multiple rule. Because you times this constant, then you bring it in front, and then you take partial derivative this with respect to x. But this is e to this function of x. Then you have to use the chain rule. So it will be this exponential function itself, so e to the x times y, and then multiply by the derivative of this inner function with respect to x, which is 1. So this is how you got this, right? Good. Okay, similarly, what's f of, what is the partial derivative with respect to y? Isn't it very similar? The x and y here is actually about this, the similarity between the x and y. So regarding this, okay, can you tell me what would that be? So that would be what? Ln of z times what? E to the x times y times what? Times x. Yes, you got it. You can change in different order. You can put it as x e to the xy times ln of z, if that looks better. Okay? Okay, good job. Now, what about partial derivative with respect to z? Now, e to the xy, we got as a constant, right? So we'll have e to the xy here in front, because we can think about it. It doesn't involve z, so we think about it as constant. What's the derivative of ln of z? This one doesn't have the absolute value. 1 over z. Okay. Yeah, you got it. So it's 1 over z. So when do you have absolute value? It is the antiderivative of 1 over z. Yeah, that one has absolute value. But when you differentiate, it doesn't. Okay. But good point. I'm glad that you pay attention and be careful with that. Okay. So that is the partial derivative. Okay, you guys have done a lot today.